Over a 24-hour period, 145 billion emails are sent, some 4.5 internet searches. Every day we generate 2.5 trillion bytes of data. These astronomical numbers are so hard to conceive that the computer sector had to invent its own scale based on the byte. A byte consists of 8 bits, representing zeros or ones. Therefore, a single character of text corresponds to a byte. 1 page, 3 kilobytes. 300 pages, a megabyte. A library, a gigabyte. 5 libraries, a DVD. 6 million books, a terabyte, or a stack of 200 DVDs. A 200-meter stack of DVDs represents a petabyte. A 1 kilometer high stack of DVDs, an exabyte, is the equivalent of all the information produced by humanity through 2003. A stack of DVDs stretching from the Earth to the Moon represents 1.8 zettabytes, or all the information produced in the year 2011. A stack of DVD linking Mars to the Sun represents a yottabyte, or the volume of digital data generated within the next 5 years. At first sight, no existing medium could store such a huge mass of data. Does this mean our societies are facing an impasse? Certainly not. Scientists responsible for storing data have understood that we now have to change our mindset. They are now looking at a device we all carry within us and that has already proved to be effective. This complex system, whose immense resources still hold many surprises, is DNA, contained in the chromosomes of all forms of life. Nick Goldman and his team are exploring this aspect of DNA at the European Bioinformatics Institute in the UK.
There's lots of reasons why DNA is a good medium. It's very, very small. It's very inexpensive. It lasts a very long time. It doesn't require any energy. And we will always be able to read DNA. So something like a floppy disk is no longer readable. In a few years' time, probably DVDs will no longer be readable because we won't have the technology any longer to do that. But DNA, we will always have some technology to read DNA. The technology changes, and at the moment, it's changing very fast. Every couple of years, there's a new machine to read DNA. But because it's the stuff in our own genomes, we will always have a new machine that can read DNA.
Nick Goldman's team decided to encode in DNA a photograph of their institute, a text on genetics, some Shakespearean sonnets, and an audio file of Martin Luther King's famous "I Have a Dream" speech.
In Alabama with its vicious racists.
The challenge was to move from a computer language consisting of zeros and ones to a much more complex genetic code that involves not just 2, but 4 components. The 4 DNA molecules symbolized by the letters A, C, T, G. These 4 elements came together at the bottom of the oceans millions of years ago to create the vocabulary of life. The famous DNA double helix is certainly the first code that ever existed on planet Earth.
But with DNA, we have 4 letters that we can use. And it's like looking at Lego, where I have 4 colors of blocks. And I can put those together in any order to make a message. And we devised a code that would use different, it's like colors, but letters of DNA. And each little block would represent 1 byte or 1 small part of the signal. And then we can put those together in any order to make the larger signal. And we devised a code that would do this but would minimize the number of errors that would happen due to reading and writing DNA.
Nick Goldman and his staff started with the zeros and ones encoding the photograph, texts, and the audio file. They then applied their mathematical code to switch from this binary language to the 4 letters ACTG, forming the DNA code. The photograph, texts, and speech were then fragmented into thousands of DNA segments. These were then reproduced chemically. At the end of the process, the original digital message is recorded on thousands of inert artificial DNA strands.
Now the DNA holds the information in physical form. It looks like it's empty, but there's a tiny speck of DNA in there, and we sent that to the laboratories in Heidelberg to be read.
At this point, genetics takes over from digital processing. To test the process, the strands were sent to the European Molecular Biology Laboratory in Germany to be decoded. Biologists placed the DNA strands in sequencers. These instruments will read the combinations of the 4 letters ACTG.
Imagine the data which are produced in large research facilities like CERN or here at EMBL. Then you have to find a proper way to store it, or at least to archive it in the first instance. Otherwise, all the scientific progress we are doing in the near future, we can't access it anymore. It starts already that our society is losing knowledge. And actually, I think that the research on DNA storage is one of the really promising fields in this area.
Another advantage of DNA, it is a solid material that stands up perfectly to transport.
To store DNA, you have to really consider 3 parameters. The first thing is to have to keep it cold, and you have to keep it dry, because this is preventing any chemical reactions around. The third thing is you should prevent it from light.
It is therefore not surprising that the frozen dry ground of Siberia was perfect for conserving the DNA fragments of animals that had died thousands of years ago.
About 1 year ago, a scientific paper was published studying the genomes of ancient horses, and they had samples of DNA that had lasted for 700,000 years, and they were able to successfully read back much of that DNA. So that's an experiment that has already been done that shows that DNA can last holding an information, holding a signal for more than 500,000 years.
It took the German team nearly 2 weeks to decode all the DNA sequences sent by the British Research Institute. All the DNA strands were read, and all the messages were fully retrieved.
After we received the sequence read information back from the Heidelberg laboratory, we decode those fragments of DNA and we put back together the binary files based on that information. And then we want to compare whether that exactly matches what we started with. So the photograph looks exactly the same. And we also checked in the computer whether every single bit, every 0 and 1 was correct, and it was.
I have a dream that one day, down in Alabama, with its vicious racists, with its governor having his lips dripping with the word.
Nick Goldman and his colleagues demonstrated that encoding digital information in DNA strands is a perfectly realistic alternative that could also offer large storage capacities.
So using the same system that we used in our experiment, the full size of all the information in the whole world is 2 cubic meters. So that's 2 meters by 1 meter by 1 meter. So you could fit that all in the back of a large car.
For now, the process is still experimental, as it is complex and expensive. Yet it is conceivable and within the realm of possibility that in the future storage sites could archive millions of test tubes containing the strands of DNA memory.